For elastic collisions, two objects will collide and bounce off each other, and both momentum and kinetic energy are conserved. So we have object A moving this way, object B this way, they strike, then they move apart. We are now going to have two simultaneous equations to solve, the conservation of momentum and the conservation of kinetic energy, to predict their motion after the collision. So the math is going to ramp up just a little bit. Let's begin the math. Here we have the before situation, two objects moving towards each other and then they move apart. Our conservation of momentum, we wind up with ma va plus mb vb equals the same thing on the right side, just with the primes indicating the final velocity. For kinetic energy, we go back to 1/2 mv squared, and it's very similar. We have the left-hand side without the prime velocities and the right-hand side with the prime velocities. Since both of these equations, the conservation of momentum here and the conservation of kinetic energy, describe the motion of the same system, they both must be true. Hence, they can be solved as simultaneous equations, or you may have heard it as systems of equations. And also just notice a little notation change. We've been using A and B for the two particles. Now we're switching it to 1 and 2. This just helps you get familiar with various textbooks, various websites that will use either one. Either one works. Now for some fun algebra. Here's our conservation of momentum. The first thing we're going to do is get all the terms with m1 on the left side and m2 on the right. So I have m1 v1 minus m1 v1 prime equals m2 v2 prime minus m2 v2. And the reason we did that is our next step is we factor out the masses. So we have this equation here after just a little bit of algebraic manipulation. The kinetic energy, first thing we do is blow away the 1/2. We just multiply everybody by 2, they go away. And then we use the same trick we did over here. We get m1, all the terms with m1 on the left side, all the terms with m2 on the right side. Then we factor out the masses. Now let's look at this here. Does this look familiar? And here's another hint. Don't look at the masses, just look at this term right here. Hopefully somewhere in your algebra that should be ringing a bell right now. So take a second and think about it, and move on to the next slide when you're ready. We'll repeat where we got to with the last slide. Here's what we have from conservation of momentum, and here's the conservation of kinetic energy, and you were asked, does that look familiar? One of my favorite things to factor is right here. If you have a squared minus b squared, that's equal to a plus b times a minus b. So in this case, the role of a is taken by v1, and the role of b is v1 prime, or v2 prime and v2 in the second case. So we're going to factor this out into this expression here. So now I've got two equations that I'm working with, one from kinetic energy, one from momentum. And what we're going to do now is cool. We're going to divide the conservation of kinetic energy equation, that's right here, by the conservation of momentum equation. You can check with your math teacher there, that's totally acceptable. We divide our two equations now. Top part we got from the conservation of kinetic energy, and the bottom from the conservation of momentum. Can you see anything that can be canceled? Well, on the left side, let's just draw a line here. The left side, m1's cancel. This term cancels. On the right side, m2, and this is why we factored out the m's in the first place. And then this cancels out. So we're left with v1 plus v1 prime equals v2 prime plus v2. We do one more rearrangement where we put the initial velocities on the left side and the final on the right. You can go ahead and check the math, it should work. This is what we were looking for, this result right here. What do they mean? What do those terms mean, the ones on the left and the right? The terms are the relative velocities of the two objects before and after the collision. Relative velocity is defined as the difference between two velocities. So this is the velocity at which, this relative velocity is the velocity at which the particles get attracted to each other, come closer to each other, and this is their relative velocity as they move away. Note that for all elastic collisions, independent of each object's mass, you don't see a mass term up here, so it doesn't matter. The magnitude of their relative velocities is exactly the same. The direction is the opposite direction because of the negative sign, but the magnitude is the same.